Hello everyone. So I am Akriti Chandra
And I'm Sandra.
and we are team Apne Pair Pe Kulhadi Marna and our project topic is secure and scalable row hammer mitigation. So first of all, what is the goal of our project? It is to implement a row swap mitigation because it has been found that randomized row swap, which is a previous mitigation, could be broken by juggernaut attack within one day. And we need to make the mitigation scalable to enhance the performance. And we also wanted to implement attack detection for attacks like juggernaut. We also wanted to try that if we could execute some mechanism to improve overheads over the SRS that we are going to execute.
So what randomized those swap does is it tries to mitigate row hammer by swapping aggressor rows with some randomly chosen rows in the memory before it can induce any split flip. So we have a bank here with an aggressor row. So after a minimum threshold of say TS activations, it finds a random row in the memory and swaps it with the aggressor row. Now, when we activate the same physical address again, TS times, it has to swap again. But it doesn't directly swap, it first unswaps it with its original location, which causes a latent activation. And then it swaps the contents with another random row, which again causes another activation. These are two latent activations that are caused due to one attack round. So this is exploited by the Juggernaut attack, which renders RRS useless.
So let's see the Juggernaut's exploitation through an example. So as discussed earlier, we have a threshold, row hammer threshold. We have number of activations after which the row will be swapped by RRS, that is 4800 and 800. And there will be a number of attack round, which is 800. And n is equivalent to the aggressor row's unswap and swap operations. So total latent activations comes out to be 2 times n plus 1. And apart from that, for our initial swap, that is the 2 plus 1, that one thing, we need to do TS activation for that initial swap. So for that, we have furthermore 800 activations, due to which by repeatedly accessing the same aggressor row again and again, whether its data has been swapped or not, for those n rounds, we got uh, 2400 extra activation as a result of latent activations. So after which we are left with only approximately 2400 more activations to reach the TRS threshold within the specified 64 millisecond time interval. So there is a second part of Juggernaut, which is the random guess attack, which randomly guesses whether the row is the correct aggressor row or not. And during that time interval, if we get three times correctly the correct aggressor row, then we will be able to cross the TRH. And since the swap rate is 6, which is greater than 3, which is the required time we want the correct guess, the RRS is easily breakable. And we uh, through our like through our sample rounds for the artifact provided by the code base for this RRS attack, we did find out that the number of attack rounds, uh, if it is increased, then the required number of correct guesses is reduced. And also, if the TRH is lower, then also the number of correct random guesses is reduced.
So the main culprit in breaking RRS was this unswap swap operation. And in SRS, that is secured row swap, we eliminated. So in both RRS and SRS, there's a row indirection table which stores the mappings of all the swapped rows. So there's it maps the address to the physical location. So in RRS, it's pretty straightforward because as we can see, there's a pair of swapped rows here, and when B is again activated TS times, it will have to um, reswapped. So it unswaps and that entry is eliminated from the RIT. And then B can be swapped with some other location. But in SRS, what we do is we don't unswap it. We directly swap row B with some other row C, and we store that mapping in the RIT. So um,
To which we don't.
and in the RIT, the RIT here is partitioned. Um, the so it stores the real mappings and the mirrored mappings as well. So the reason we were using unswap operation in RRS was to maintain memory organization and thus maintain performance so that there's no latency in lookups. So, what we do in SRS is we do lazy eviction in the RIT to have the same effect. So, lazy eviction basically stores the rows one by one back to their original position. Suppose we want to store row back to its original position. So what we do first is we store the contents of Ruby in the swap buffer. Then all the mappings in the RIT about row B are eliminated because it's not in the bank. Now row is placed in a place pack buffer, which is an extra storage overhead that we have introduced. Um, and its mapping is also updated. Now row B can go back to its original position. Similarly, we place row C in the swap buffer, and now row A can go back to its original place, and then row C can go back to its original place. And as you can see, all the RIT mappings are updated.
So SRS is basically punish the attacker. So in this, uh, it's a mitigation technique where we make it difficult for the attacker. Even though if SRS is breakable, it will break after 2 years, whereas RRS just breaks in 4 hours. So this makes SRS better than RRS. But there is an issue that the performance of RRS and SRS is almost the same because of the same memory bandwidth overhead, because of having the same swap rate, and also SRS having almost half the accessibility to RIT table. So let's first look at the detector. And for the detector, we have a counter for swaps, for which we have a 32-bit counter per DRAM row, which is divided into 19-bit EPO ID to keep track of each EPO, and 13-bit activation counter. So it could count 8192 activations in one go. And if EPO ID is equivalent to on-chip EPO register, then the activation counter is increased. If the EPO ID is not equal to on-chip EPO register, that means that a new EPO, like 64 milliseconds, had been stopped, and we need a new count. We need to reset the activation counter. So within the EPO, 64 millisecond, if we found that the counter is more than the TRA, then the row is flagged. It means that the row can't be used as a swap option by the SRS. So due to which we will be able to reduce the swap rate as well, which would make the SRS scalable. For that also, we have created a pin buffer that only redirects to rows that are activated beyond the safe threshold. Suppose our threshold is 3 times TS, then if the row has activation more than that, then it's flagged. We can't swap to that row, due to which the potential rows for swapping, which could be guessed randomly, is reduced to around 1000 in this case. And we have fifth mapping in cache sets for this. For this, we use the LLC cache. And we have a compact size buffer, which is like, suppose we could have a 66 entry buffer, and then we could evict, because we don't need to track thousands of rows for it. We have already found out that these rows are more vulnerable to be aggressor rows, then why do we keep it as a swap option? So, and also, it has been found that if row A was swapped to a new location in a cycle, then there are very less chances that we could have the same mapping in our table. due to which we implemented our scalable SRS, and these are the results that we got. A major breakthrough in comparison to RRS and SRS was for the lower TRS, which was suppose in this case 5112, where for every benchmark we got that the lower TRH performance level of RRS was quite lower in comparison to SRS. Overall also it was very lower, but the major breakthrough was seen over lower TRH, which is more vulnerable to attacks, but SRS, scalable SRS even gives better performance for that. Thank you.